So today, let's go to the section 4.5, recycle and bypass. Recycle and bypass. So I'm sure you all know these figures because you just had this for your midterm exam. So the thing is that we have a mixture of water and acetone, and we want to separate water and acetone. So the strategy is not we all understand that we cannot use distillation column to separate water and acetone because they have low boiling point and also their boiling point are very close. So before we use distillation column, we need to use another strategy, or we need to use another process called extraction, liquid extraction. So we introduce MIBK into the extractor. So MIBK will take away acetone from water, right? So we will have two streams. One stream is rich acetone and MIBK. One stream is rich with water. But unfortunately, because the separation process may be not so efficient for the first extractor, so we use the second extractor. Again, we introduce NIBK into this extractor in order to get a more pure MIBK and acetone. So, and then we take the raffinate we take the extractor back here, and then we use the distillation column to separate MIBK and acetone. So as a result, we got water here, and then we will have products, which is acetone. And then finally, we have MIBK. So water can be discharged to the river or somewhere, okay? Or you can reuse. And products, that means that we have this products, which is about 97% purity, and we can use it for another purpose, okay? And then how about MIBK? MIBK can what? Can use again into this process, right? That's better, right? You might say, "Oh, Professor, wrong. I want to have 100% purity of MIBK into extractor 1 and extractor 2. Is this necessary? No, this is not. Why? Because you don't need very high purity of MIBK and to do the extraction, right? So you are allowed to use a very small amount of the water and acetone into this extractor through this stream, right? So this is the meaning of the recycle. Okay, so what's good about recycle? Okay, so this is another case showing you here. For example, this is a reaction. Of course, we will have a reactor. So it is rare that a chemical reaction A to B persists to a completion in a reactor. So if you want to have a 100% conversion rate, you might need a very good reactor. But well, that might be very expensive. But if you want to have you don't need to have a very good reactor. The conversion rate might be say 80%. That will be enough because that's less expensive. It might be very, very cheap. So as a result, if we have A into this reactor and come out with A and B, which A might be 20%, B might be 80%, and we are not happy with this product, then what's the next? If we are not happy with this product, we will have a separator, right? If we are able to separate A and B away from each other, then we have done a good job, right? So this separator, we have product which is B, and we can separate this separation very well. So we have a pure B. And what happened to A? The good thing is that you don't want to discharge A. You want to recycle A. Well, you might have a little bit B here. It doesn't matter, right? You will recycle A back to here and feed into a reactor. So this is called recycle stream. Recycle stream. And then recycle back A to the reactor, which is good. So recycle is that what could so recycle is that before in order to have a very good reaction, we need to have a very good reactor. However, if we don't have a very good reactor, you might need to build a separator to separate A and B. So pay the separation and the recycle equipment. You need to spend money for this. If you don't want to have a very good reactor, you need to spend money for this. But if this money is very cheap, then it is worse, right? It is worse. So purge less, and also the other good thing is that you purge less fresh reactants, because the fresh reactant is here, so you have a combination with recycle stream. So you feed less reactants, save money, okay? And then being able to sell the purified products as a higher price. Is purified product as a higher price. So this is good. Okay, so before we talk about mass balances, so far I already told you there are two reasons to have a recycle stream. The first reason is that in the previous slide, you have MIBK to recycle. You want to use the MIBK efficiently. Okay, so you recycle the stream and save money, and make the price save money, and then make the process more look smarter. Okay, the second reason for the recycle is that if your conversion rate of reactor is not that good, so you need to build up a separator. And if separator is very cheap, then you pay less, right? You pay the separation and the recycle stream, but if instead of building a very expensive reactor, or build another reactor, for example. Okay, so this is what we call recycle stream here. So again, we need to talk about, once we want to do mass balances, we need to talk about the systems, right? That's what you already know, you have learned, and you have practiced in your midterm exam. So let's talk about system. The single unit system, how many single unit system here? This can be regarded as a one single unit system, because this is a joint stream. This is a joint stream. So it looks like a mixer, right? Flash input and recycle stream, they mix here. You can regard this as a mixer. So we have a one single unit system here. So how many input and how many output? There are two inputs, one output. Okay, and then what's another one? Single unit system. This is another one called single unit system. Reactor, one input, one output. Okay, and the third one is separator. The third single unit system is separator. So how many input and how many output? One input and then two output, right? Right. Okay, so we have three single unit system. So how many two unit system? Two, right? One and two. You might say, Professor, can I write this? Yes, you can, but normally it looks a little bit complicated. Okay, so overall system is this one. Okay, this is overall unit systems, right? Okay, right. So now let's take a quick look of these figures. 4.5-1 recycle A and to B. Again, let's say this reactor here, and we have a separator. Obviously, this reactor is not very good. The conversion rate is low. So that's why we need a separator. So we have 200 kilograms A per minute and 30 kilograms B per minute. And this mixture will fed into the reactor. And then we have 100 kilograms A and per minute and 130 kilograms B per minute come out from this reactor. So as you can see, A reduced, B increased. That's the reaction like this, right? Okay, and you know that the conversion rate is not that good. Might be 50% conversion rate only. Okay, this is 50% conversion rate. So, and then let's separate this product and B and A. So we have B and A. So you might say the separation efficiency might be like 90%, right? This is 90%, okay, purity, something like this, around 90%. So the separator is not that good too. So you might want to build another separator, but it costs money. So you need to judge which one is better. Okay, is the market allow these products? The purity is about 90% purity of the products. If the market accept this this number, like 90% purity, then you can sell. If market is not allowed, if this purity is not accepted, then you need to have a better separator, right? Okay, so now this is the one recycle stream back to this stream. So this is called recycle stream. And this is a joint point, which is this 90 kilograms and 30 kilograms per minute, A and B, together with the fresh feed, which is 110 kilograms A per minute. So originally, you just feed this one into this reactor. But if you don't have recycle stream, you need to feed this. So you feed less compared to if you have a recycle stream, you feed less fresh feed into this reactor. Okay, this is one of the examples showing you that the meaning of the recycle streams. Right. So now let's practice this example 4.5-1 material and energy balances on an air conditioner. You know air conditioner, right? Air conditioner is the one we are having now here. So we have air conditioner, and then we have fresh air going to the air conditioner. Like, you know, the air in this environment, the air conditioner suck the air into this from this room, and then assume this fresh air has about 4% water, and then 96%. DA stand for dry air. Okay, so you have 4% water. Obviously, this amount of water is too much. You don't feel comfortable. So you want to have less air. So you make this room feel more comfortable. You can stay here better. So the air fed into the air conditioner and then come out, right? Come out. And then we want the air in the end, we want the air come with 1.7% water only. Obviously, you know, dry air will be 98.3%. Okay, this is the purpose. However, if your air conditioner is not good enough, there's no point. If this air conditioner is not good or too small, then this air conditioner cannot deliver the quality of the air like this. Okay, because the conversion rate is not high enough. Then what happened? For example, like this, you need a bigger air conditioner, or you need to engineer this air conditioner. And a good engineer will do something like this. Oh, sorry. This is the water come out. Okay, water come out. So as you know that air conditioner always will have a pipe, and then the water will come out from the pipe, right? Okay, so again, I want to tell you that if this air conditioner doesn't work to let 90% dry air become 98.3% dry air, So the reason is that this air conditioner is not good enough. Either you buy a new air conditioner to make a good conversion rate, or you do engineering like this. You get some of the dry air out and then recycle back to this fresh air. Mix it together. Why? Why we need to do this? Why we need to do this? That's because you dilute the concentration of the water. You dilute the concentration of the water to make it become less water. So assume this water, the joint point here deliver 2.3% of water only. And of course, you have 97.7% dry air. So as you know that if you dilute the water, that means you have a more dry air. And then the conversion rate might be good enough. You might be able to take out a certain water away from this input stream and deliver this kind of quality of the air. Okay, this is the meaning of the recycle. So this is called recycle stream. And then remainder is that I don't have time to read this for you, but 4.5-1, they come out with 100 moles per minute, something like this, okay, of this quality of water, something like this. Okay, so now this is all the information we know from this example. So now let's write down we already put all the knowns in this flow chart, and now let's put the unknowns in this flow chart. So for the fresh air, we have we have fractions, and they are only air and water, right? So this is the total moles of the air of this air, right? This fresh air, N1. And of course, you know that for this joint stream here, you have N2. So this fraction, 97.7 dry air and 2.3% water. Okay, and then and this air go into the air conditioner and come out with water. Water is in liquid, right? In a liquid form. So you have N3. Okay, the problem now is that how do you address this stream here? That will be N4, right? N4. And how do you write down the fraction of the dry air and the water? The fraction will be the same as this, right? So recycle stream, a very important point for this is that the fraction will be the same. So what I want to tell you is that the fraction of this stream will be the fraction in this stream will be exactly the fraction in this stream. Why? Because this stream split into two. One is output, one is recycle stream. So there's nothing changed in terms of the fraction. So 98.3 dry air and 1.7% water here. So as you can see that I didn't put red color in this number. Okay. So this is not unknown, this is known. And then recycle stream, you have what? Yeah, N5. And again, the fraction will be the same. What is 1.7% water, 98.3% dry air. Okay, this is how it looks like. So we finish all the, we address all the unknowns in this flow chart. Okay. And you need to understand the meaning of the recycle here. Okay, so can we solve this problem? Can we do this? First of all, choose of the basis, right? Basis is 100. And then draw the flow chart. We draw the flow chart, and we address the knowns and address the unknowns. Okay, important thing is that the fraction here will be the same, exactly the same as in this stream, output stream, and recycle stream. And we have 5 unknowns: N1, N2, N3, N4, and N5. Right. So next step is DOF. Again, we do DOF systematically. First of all, do single unit, right? First of all, well, here is overall. Again, anyway, overall. Let's do overall first. How many input and how many output? 1 input and 1 output, right? Sorry, 2 output. How many unknowns here? There are 2 unknowns, right? So overall system, we have, and then mixing point here. So can we solve the problem here now? N1 and N3? Yes, we can, right? Okay, then mixing point. And then air conditioner, 1, 1, 1 here. And splitting point. Mixing point, air conditioner, splitting point. Okay? So overall system, we have 2 unknowns. 1, N1 and N3, right? And how many equations we have? We have 2 species, right? 2 species, dry air and the water. And then we don't have specification. We don't have physical laws, physical constraints. So anyway, 2 unknowns. We have 2 equations. Bingo. We can solve out N1 and N3. Okay. So here, we can change this symbol from red color to blue color, and this one from symbol from red color to blue color. So we can easily get these 2 numbers, get these 2 unknowns because of 2 equations. Okay, so this is overall system. Let's go back to the single unit system. So we get this N1 and N3 here, and then we have N, and then let's go back to N mixing point. Mixing point is here. So how many unknown? How many input and how many output? 2 input, right, and 1 output. Okay, and then how many unknowns here? We have N5 and N2. We have 2 unknowns. And how many equations we have? We have 2 equations, right? Dry air and water. So you have 2 unknown, 2 equations. Bingo. We can determine N2 and N5. Okay, so N2 and N5, I'll change these 2 symbols from red color to blue color. Okay, right, let's go, and then let's go to, after mixing point, let's go to the air conditioner. We only have 1 unknowns. Obviously, this is quite easy, right? Quite easy. So let's do it. N4, bingo. We solve the problem. Okay. So I don't want to waste your time. So please do this calculation by yourself. So, and the last thing we need to discuss is if there is no recycle stream here, and because the air conditioner efficiency is low, so the concentration of the output, concentration of the water in the output stream will be what? Will be increased, right? We cannot reach this number because if there is no recycle stream, we only can reach this number using the recycle stream. It's like a dilution, right? You know, you cannot drink soybean sauce, right? You cannot drink soybean sauce. 酱油, can you drink that? You cannot, right? You need to dilute, and you can drink, right? Okay, that's one of the example, which is not quite exact example to explain, but anyway. So the reasons for recycles, this might be in your Kahoot in the following week. The reasons for using recycle: 1, recovering and reusing unconsumed reactants, right? Recovering is that MIBK recover, right? You come back, MIBK come back, and reusing unconsumed, right? You have reactor here, unconsumed reactants. First reason. Second, dilute of the process streams, like dilute. You know, this one dilute, right? Recycle, dilute is fresh air, the water in the fresh air. The second reason, I already all explained this to you. Third one, recover of the catalyst. Catalyst is a kind of solid material which is basically is expensive. Like fuel cell, there's a catalyst. Fuel cell is very expensive. So recovering of the catalyst, normally you know this reason. And the fourth one is control of the process variables, like capacitance for the heat released. This is nothing to do with mass balance. It's nothing to do with mass, but also something to do with energy. Okay, the last one is also related with the energy. I don't have time to explain this to you, but what I want you to know so far is you need to remember the first three reasons. Okay, first three reasons. And the last two reasons are all related to the energy. Right. So the last, this is another example, evaporation, boiling, and filtration. So can you tell what's the differences with the evaporation and boiling? Do you know the definition of boiling and the evaporation? Right. So evaporation is look like this. If you have a pot of water and you heat up the water, and you can see the stream come out. But actually, the temperature hasn't reached 100 Celsius. And the water already come out. Eventually, water will reduce gradually. Even though the temperature go to 60 or 70 Celsius, the water keep on coming out. This is what we call evaporation. What's the boiling? Boiling is that the temperature go to 100 Celsius, right? Okay, this difference between the boiling and the evaporation. Both the water will come out from the water molecule will come out from the water, liquid water, and become a vapor. Okay, but you know when you increase the temperature to 100 Celsius, boiling will be the water come out from the liquid water will be much faster, right? So this is the definition of the evaporation. Evaporation is a type of vaporization of a liquid that occurs only on the surface of a liquid. The other type of the vaporization is boiling. So there are two types, right? Well, first type is evaporation. The second type is boiling. That instead occur on the entire mass of the liquid. So you understand boiling is that it happened, vaporization happened on the entire mass of liquid. I have a very good picture for you later, in the next slide, so it will be easier for you to understand. This is the process by which molecules in liquid state spontaneously become gaseous. Right? So you want to make something in gas phase from liquid, and this is the technique, or this is the process you need to apply. You need to employ. So what's the difference between evaporation and boiling? Evaporation is something to do with the surface of the liquid, right? So the water molecule come out from the surface of the liquid. And the boiling is that the water molecule come out from the entire mass of the liquid. Okay? So, you know, when you do this is the chemistry. When you do it in the chemistry laboratory, when you understand the meaning of evaporation, this is one of a very good example. So how you do this in engineering process, in industrial process. The industrial process evaporation, we call a very good evaporator. So there are many types of the industrial evaporator. I don't have time to tell you all, but here I just give you one of the example. So you have a mixture of A and B, and you want to evaporate B, or you come out. So you have your mixture will pour into the top of here, of this tower. This is a very big tower. If you take a close look of this tower, this mixture will go into this tower, and then there are many small pipes. Many small pipes. And the water, this mixture of liquid will go into this pipe, just along the surface of this pipe, inner surface of this pipe. So you don't want to pour all, and then when this liquid go into the surface, the edge or surface of this pipe, it will drop, it will flow down, right? It will flow down. And here you have steam. You increase the temperature here. Let's make it larger. You increase the temperature up here. For example, you can go up to 400 Celsius, 300 Celsius, for example. So you input the stream come here, and the inner of the pipe, the temperature of the pipe will increase, as well as the inner fluid, liquid in the pipe, right? Okay, so as a result, you come up with two things. The first is liquid. It will drop here. Second will be vapor. Vapor will be collect here. And you just cool it down. You just cool the vapor down, and it will become liquid again. So you have a good separation using evaporator. So if you have A and B, you put it here and adjust an appropriate temperature. And then you can make B become vapor. And if B become vapor, the B will be here, A will be here. This is the industrial process of the evaporation. So because the example 4.5-2 is evaporative and crystallization process. So that means that you have something you make the mixture, or you make the liquid become slurry, and you want to separate a slurry. And if you want to separate a slurry from liquid to solid, the way you need to use is called a filtration. I'm sure you have learned this when you are in high school or junior high. You know, when you want to separate solid and liquid, the way you use is called filtration. So you have beaker here, and you put the things. For example, you put a mixture like this. Water will go through this filter, right? And then, for example, this silicon dioxide, for example, will be blocked on the surface of the membrane of the filter. So you have a solid and liquid separation. So this is the way, and you suck the air from here, so you make the separation more efficient. So this is, you have a pump, and you suck the air from here, so air will be, and you can do the separation here. This is what you do when you are in high school or you are in the chemistry laboratory, right? So how are you going to do this in an industrial scale? If I want you to separate in 1 ton per 1 hour, or 1 ton per for 1 day, can you do that using this beaker? No, you cannot, right? As I hope you still remember in the first lecture, I told you that if you want to make penicillin in industrial scale, you cannot use beaker to shake, right? This is not a good thing to do. So that's the meaning of the engineer, right? Okay, so let's define what is the filtration. Filtration is a mechanical or physical operation which is used for the separation of solid from fluids. Fluid can be liquid or gases. Okay, by interposing a medium through which only fluid can pass. So intermediate means what? The filter, right? This is filter. So this is what we call solid-liquid separation. Okay, and then you need help from the vacuum, and we call this vacuum filtration, which make the separation more efficient. So this is industrial way. One of the industrial way we call rotary vacuum drum, rotary vacuum, or we call drum filter. Drum filter. You know, this scale is huge. As you can see, the scale, the human being here, and this is a very big drum, right? Rotary drum. Okay, this rotary drum, vacuum drum, rotate like this way, and you have a mixture of liquid and solid in this place. This is the cross section, okay, of this drum, okay, and you move like this way, and you have suction, like you use a vacuum in the center, so vacuum will suck, and you have a close, you have a kind of close on the surface of this drum, and because you suck the air into this place, so the air, the water will be sucked in, and the solid will stay here. As you can see, this is what we call cake. It's not what you eat at home, okay? This as a cake, birthday cake or something. No, this is a cake which is solid, and you can see that this cake from the thickness of the cake from thin to thick, and then this is the product you want, and you need water to wash this cake, okay? And then this as it rotate, it's getting thicker and thicker, and then you need to dewater, right? Because you wash these products and dewater, and you have a knife. You have a knife here, a blender. A knife will take out these solid products, so you get this. You get the products. This is the industrial filtration. You can do this, you know, you can do this continuously, right? Now, this before we move to the text of this, I want to work on this. I want to practice this example with you step by step. But we need to read the text. So I want you to get the text ready. So I can read the text with you, and we can go through this example very well. You know, this is the example tell us that a combination of the evaporator and the crystallizer, or we call filters. So actually, you just think of, you have this in the first one, you have this in the second one. That's it. Okay, and then you have recycle stream. Why? Because as you can see that water come out, and you can recycle. You can recycle these streams, right? And so you get cake out, and cake there's two streams, because in the textbook, in your book, there's only one stream. That stream is that the cake, solid cake with water. You know, the cake always wet. So the cake has divided into two. One is solid, one is liquid. So that's why I wrote two streams here. But actually, there's only one stream, which is cake. And you have water come out. You have liquid come out from here. It can be water. It can be acetone. It can be alcohol, for example. Okay, so this is the flow chart. The flow chart looks like this. So now this, please work with me, and let's do this one by one. And if you have book, that will be in the page 104. And if you have a lecture note, please let's work together. So the flow chart of the steady state process. Steady state process means what? There's no accumulation. You know, we have 5 terms in the general balance equation, right? Input, output, generation, consumption, and accumulation. So if this is a steady state process, then that means that there is no accumulation terms. Okay, process to recover crystalline potassium chromate. Potassium chromate is a kind of chemical. Okay, it's K2CrO4 from an aqueous solution. Aqueous solution means water, right? Because potassium chromate solute in the water. So you want to take potassium chromate away from the water. So of this salt is shown below. Right, so you have numbers here. You have numbers here. Okay, so let's read first. The 4,500 kilograms per hour. So this is continuous. This is a continuous process, right? Because per hour means it's a continuous process. So if this is a continuous process, you can remove accumulation. You can not only remove accumulation term, but also remove generation and the consumption term, right? So the general balance equation become input equal to output because there is no involved chemical reaction. Okay, so where are we? So the 4,500 where are we? Okay, 4,500 kilograms per hour of the solution that is 1/3 potassium chromate by mass. What is 1/3? What is 1/3? 1/3吧，是不是 1/3 是1/3？那 2 out of 3呢？2 out of 3， 2/3吧，是不是 ？Okay, good. So 1/3 potassium chromate by mass is joined by a recycled stream containing 36.4% potassium chromate, and the combined streams is fed to an evaporator. This sentence sounds complicated, but actually it's not. So if we take a look of this, please work with me on this slide. That means that we have a feed solution here, and then we understand that the feed stream go into here. Because potassium chromate, right? So goes through the evaporator, and we take out water, and it becomes the concentration will become the concentration of the potassium chromate will become higher, and this is what we call slurry. 泥浆 slurries look like 泥浆, right? So this is solution, it's like water, and because we use the evaporator, it becomes slurry. If we are slurry and go through this filtration, so we can make a cake and then take out the rest of the water, and we feed the rest of water back to this evaporator. It's kind of dilute, right? Dilute. So this filtered cake is a combination of the potassium chromate in solid and as well as solution. But I want you to remember that this solution still have some of the potassium chromate, because potassium chromate will dissolve in the water. So you cannot discharge this to the river. No, you cannot. Otherwise, you go to jail, right? You break the law, like some of the industry. So you need to recycle this to make it better, to recycle potassium chromate. Okay, you cannot discharge this water because this contains potassium chromate. It's kind of toxic chemicals. Okay, so and then we have to recycle. We call filtrate, recycle back to this feed solution. And then we have 4,500 kilograms per hour, which fed into this reactor, this separator. Okay, and then let me see that. So in the book, and this is we know that we just learned, right? This is 1/3 of the potassium chromate into this solution. So it's 33.3% potassium chromate and 66.7% water. This is what we know, right? 1/3. And then we also know that it come out with that 36.4% recycled. So we understand this is the one recycled potassium chromate. That's all the information we know, right? All the information we know. Okay? And we understand that if you have 36.4% potassium chromate, that means you have 63.6% water. Right. Okay, let's read the text again. In the second paragraph, life in the end of the in the middle of the life 3, this stream is fed into the crystallizer in which it is cooled, causing crystals of the potassium chromate to come out of the solution and then filtered. That's what we know, right? Okay, the coming sorry, I think I made a mistake. The second paragraph, line 2, the end of line 2, the concentrated stream leaving the evaporator contains 49.4% potassium chromate. This is what we need to know. So let's take a look of this in the slide. Where should we address this? Here, right? Here. Right? 49.4%. Sorry, here. I'm sorry. 49.4% come out from this evaporator. Right? And this stream fed into the crystallizer and filter. So this stream is fed into the crystallizer in which it is cooled, causing the crystal of the potassium chromate to come out of the solution and then filtered. Right? This is filtered. Right. Line in the end of the line 4, the weight filter cake consists of potassium chromate crystals, and the solutions contains 36.4% potassium chromate by mass. Right. So the information tells us that here in the slide that you have the concentration of this potassium chromate, and the concentration, the solution is about 36.4% potassium chromate. Of course, you understand there are 63.6% water. So actually, filter cake is the combination of potassium chromate and solution. So I draw 2 streams here instead of 1. That will be easier for you to understand. But in your textbook, in your book, you only have one stream here. Okay, let me tell you in Chinese, that might be easier for you to understand. 这个 cake 里面有固体的，也有液体的，对不对？湿湿的嘛，对不对？湿湿的固体里面就有液体，那个液体呢，基本上就是 solution。那 solution 是饱和溶液，对不对？是 potassium chromate 的饱和溶液，是不是？所以它基本上的饱和溶液基本上就会跟这个一样嘛，是不是 ？OK， right， back to English。Right. Okay. So that's it. So in your second paragraph, line 1, 2, 3, 4, 5. Line 5, the last 7 words of the line 5, the crystal account for 95% of the total mass of the filter cake. Right. So what does this mean? The total mass of the filter cake has 95% solid, 5% liquid. Okay, so that will be, if you take a look of the slide here, on here, so that means you have 95% of the solid and 5% solution. Okay, this is what we call the specification for spec, or specification for these 2 streams. Okay, right. So that's all the information we know. We already addressed all. Well, we already write down all the nouns in this flowchart, and then we also know there's a specification between these 2 streams. Now let's write down the unknowns. So the first one, fresh solution, here we have all the information. The second one here, we don't have the information. So we write down M1. And then we don't know the fraction of the potassium chromate and water, so we write down x1, and which is the water will be 1 minus x1. Here, please remember again, I want to tell you that there's only one unknowns in this between the water and the potassium chromate, because it's fraction, and this x1, this one k fraction of potassium chromate plus the fraction of water equal to 1. So you only have one unknowns, right? You only have one unknowns. Okay, let's move. And this one go into the evaporator, and you have water. So you have M2 here, and this is pure. This is liquid. So because potassium chromate cannot be removed by evaporator, so you only have pure water, which is good, right? Okay, and then after that you go to slurry, and we understand that we already have the information over the fraction of the potassium chromate and water. So all we need to write down unknown here is M3. M3. And then after that, this crystallizer here, we have two streams. The one stream is M4. One stream is M5. If you understand, M4 has about is 95% of the total output here. M5 is 5% of the total output, right? Because this is what we know about the specification. And this recycle stream here is M6. So we write down all the things we don't know. Okay, so this is the flow chart. We have complete the flow chart. Again, I want to tell you that the symbol I mark in red color is unknown. So basis of the calculation, we know the first one is 4,500 kilograms per hour. And draw the flow chart we did. And we mark the knowns and we label the unknowns. So there are how many unknowns here? 1, 2, 3, 4, 5, 6, 7. There are 7 unknowns. Right. So let's do it systematically. First of all, let's think of the overall system. How many inputs and how many outputs? Anybody want to tell me? How many inputs and how many outputs? One input and 3 outputs. You might say, well, Professor, something wrong. Because it's inside the circle. This stream is inside the circle, right? So you only have what? 1 input and 3 outputs. 1 input and 3 output. Okay? So we have 3 unknowns. 1, M2, M4, and M5. So how many equations you can make? First of all, you have 4 directions to think of the equations. The first direction is what? How many species? Right? How many species? Sorry. How many species? 2 species. Potassium chromate and water. And then second, specification. Right? Because we know that M5 is about 95% of the total output. M4 is 95% of the total output. M5 is 5% of the total output. So this is what we call specification. And you have 3. You have 3 unknown. You have 3 equations. Bingo. You can achieve M2, M4, and M5. Okay? See that? I do it very, very hard for you to please you. So please me, okay, in your midterm exam and final exam. Okay, so I change this color from red to blue. That means you can use this equation to get these 3 numbers, 3 unknowns, right? Okay? And then mixing point. So you already get this 3, right? You already get these 3 unknowns. And then let's go to single unit system, starting from the mixing point. How many inputs? 1 input. How many outputs? How many inputs? 2 inputs. How many outputs? 1 output. So this input, and the output, right? So you have how many how many unknowns? 1, 2, 1, 2, and 3, right? 1, 2, and 3. So you have 3 unknowns. And then you have 2 equations, 2 species, potassium chromate and water. So you have 2 equations. Do we have specification? No. The only one specification we use up, which is here, right? So you don't have a specification. You don't have physical laws. You don't have physical constraints. No, you don't. So unfortunately, you cannot use mass balance of this mixed point to get these 3 unknowns. No, you cannot. Okay, so let's move to the evaporator. Obviously, as you can see, you have 3 unknowns, 1 input and 2 outputs, right? You have 3 unknowns. Unfortunately, you only have 2 equations. You cannot get these 3 unknowns using the single unit system of the evaporator. How about this one? Let's move to the next one. Crystallizer. Crystallizer here, how many input? 1 input, how many outputs? 3 outputs. How many unknowns in this system? 2 unknowns. Bingo. You have 2 unknowns. You have 2 equations. 1 input, potassium chromate, water. You can get M3 and M6. So you can determine M3 and M6 easily. Okay, so next, whatever, you just go back to mixing point, right? Or you can go to evaporator because that will be same. That will be the same because this one become knowns. You can determine this number. So you can go to this two. You can determine this too. Okay, and then now it's time for you to do the calculation, right? So please do the calculation. Right, so why we need potassium chromate? As you can see, it looks like yellow color, right? So it's kind of, you can have, if you want to have your clothes with yellow color, you can use this chemical. Or this also is for some of the organic synthesis. Okay, it's very taxi, so you cannot discharge this to the water, to the river. No, this is against the law. Okay, so this is an example I want to show you. All right, so final topic we have 8 minutes to talk about bypass. So before the previous topic we learned about recycle, right? So we have a process, and then we have input stream and output stream. If we take out some of the products from the output stream and go back to this input stream, that will what we call recycle, right? Recycle stream. And we have some reasons to know the recycle streams. Why we need the recycle streams? What's the bypass? Bypass one, gyaku desu yo. Sorry, let me show off my Japanese. 逆わかる？逆就是相逆的意思哦，逆ですよ。Sorry, let me think of English. Right, so, for a recycle, it looks like this direction, right? How about bypass? Bypass doing this direction. Why we need to do this? You must have a reason for this, right? Why we need to do this? I'm going to tell you very soon. So the definition of bypass is that a fraction of the feed to a process unit is diverted around the unit and combined with the output stream from the unit. This sentence is beautiful. After you read this sentence, you understand this completely, right? So why? We want to vary the composition and the properties of the product. We want to vary the products by using this process. We want to change the composition and we want to change the property. Okay. So how are we going to do the mass balances using the bypass stream? The bypass and the recycle calculation are approached in exactly the same manner. Why exactly the same manner? This is splitting point, right? Splitting point. Recycle stream, you have splitting point here, and now it changed to this part, this location. And in the recycle stream, you had joint point. You know, the recycle stream, you have joint point here, and now it become here, the joint point. So split point means what? You have fraction. The mass fraction will be the same. For example, you have input splitting point. That means the fraction of this stream will be the same. That means the composition will be the same. Okay, so we do this in the same manner. Okay. So this is one of example of the bypass. See that this is the proper pipe, and this is bypass stream. So if you want to change this meter or you want to change this device, so you need a bypass, right? If this break, if this is broken and you want to change a bypass, you need a bypass, right? Or if you want to measure some kind of the properties, composition of these streams, you need this bypass. Small streams come out, you need a sensor, for example. You need a sensor, and you put a sensor here, and you in a normal time you block it, but you put a sensor here, you can have this, and then make the bypass come through this. There are many examples. You know, when your heart, the pipe going to your heart is you're still too young, you don't understand this. But if you have your grandmother or grandfather, the blood pipe is too thin, and then sometimes it block. Some of the particle block the blood pipe, cannot go through the heart, so it causes death, right? So you need to have a bypass to let the blood go through, not go into that direction, go bypass, can go to the heart. That's also called bypass. So there are some of the example I want to show you here in industrial way, or what we do in the industry. So one of the important example is called concentrated juice. The second one is mass flow controller. Unfortunately, I don't have time to tell you this. If you have time, take a look over the internet, YouTube or something. They will tell you the meaning of the bypass in the mass flow controller. The second one is called jack engine. So this is the bypass for the concentrated juice. You know, when you have the concentrated 100% pure of the juice in a can, that is 100%, right? But it's different from the 100% juice you buy in the market, in the supermarket, and taste might be a little bit different. Why? But of course, this is cheaper. Why? Because a single evaporation process is used for the concentration, but volatile constituent of the juice escape with water. So you want to take out some of the water away from this juice, and you want to ship this juice from A place to United States, or from Japan to Taiwan. Of course, you want to concentrate this. Why? You don't want to ship a lot of water from United States to Taiwan. Water is heavy, costs money. So you want to reduce water from the fresh juice, and you concentrate this concentrated juice and ship it from Taiwan to Japan, or Taiwan to China, for example. And then when the concentrated juice reach Taiwan, and then we put some water in, we dilute to make it become 100% juice. And at that time, when you taste the juice, you might feel it's different from the fresh juice. Why? Because volatile constituent of the juice escape with the water. There are some small molecules will come out once you do a concentration of the juice. That's why it's kind of flat taste. The taste doesn't feel good. You don't taste good. So at that time, you need to put some of the fresh juice back to this concentrated juice. Not only dilute, not only put the water into the concentrated juice, but also you need to put some of the fresh juice into this concentrated juice. That's why we call bypassing. So what is this? This is called bypass, right? Fresh juice come in to this process. You know, when you drink Coca-Cola, the recipe of Coca-Cola, there's not many people knows the recipe of Coca-Cola. There are only 3, maximum 5. And they don't want to tell you the recipe of the Coca-Cola. So they ship the concentrate cola from China or from United States, from other place, and back here to here, and you just put the water back, right? This is another way of a bypass. So the single evaporator process is used for the concentration. I just read this for you, okay? So please read it. You know that you have in the United States, you have orange juice. Orange juice, you concentrate, you take out the water, you ship the concentrated juice from the United States to Japan, for example, and you put the water back here. But not only put the water back here, but also need to get some fresh juice back to this, and you get a concentrate. You get the 100% juice in the market. This is one of the example. Okay, the turbine engine is that you know, this is the engine of the aircraft. The engine need air, of course, because you need to burn the engine. You need to have oxygen in the air, and you have fuel. So fuel with air will get burned, and then you get power from this engine. Okay, but unfortunately, this is too noisy. If you have if air goes through this engine very fast, it gets very, very noisy, and you cannot bear this. So there's kind of bypass air to eliminate or to make the sound less louder. Okay, so this noise produced by the jet engine is highly depends on the exit of the jet velocity. Okay, since the turbofan is the bypass cool air get mixed with the hardware, it's possible to keep the outlet velocity with the limit. Thus, it's overcome the noise problem. I have a video for you, but I think I run out of my time today. So I think, right, that's it for today. Okay. So I hope you enjoyed the lecture today, and I will see you on Wednesday.